Okay, what is up, everybody? Here we go, 8.4. Guess what we get to revisit? Where is it? Nope. There we go. L'Hopital's rule. We are revisiting that, okay? We are going to evaluate limits in indeterminate form using L'Hopital's rule, including quotient, product, difference, and powers. Okay, let's get going. L'Hopital's rule. Okay, now we know how to do the basics of L'Hopital's rule. Okay, um, we know that we are supposed to, using L'Hopital's rule, if we have one of our infamous indeterminate forms of either zero over zero or infinity over infinity, we will differentiate both the numerator and denominator, and then we will see if the limit can exist then, and if not, we continuously just keep using L'Hopital's rule. All right, so remember, we must show that the limits go to zero in the original setup, or if they go to positive or negative infinity. What's going to happen today is we're going to be presented some limits where they might not be in our familiar form of 0 over 0 or infinity over infinity. They may come in another form, 0 times infinity, 1 to the infinity, infinity minus infinity, and the ever so popular infinity to the 0 or 0 to the infinity. What's going to happen is if it is not 0 over 0 or infinity over infinity, if it is one of the other limits that you see that I've highlighted, our job is to rewrite it or possibly write an equation that can get it into that form of either 0 over 0 or some form of infinity over infinity. So let's take a look at this first, these first few examples here. Okay, here I have working with the indeterminate form of 0 times some form of infinity, a product. All right, that means we're going to want to change the product into some kind of a quotient and then just kind of go from there. All right, so example number 1, the limit as x approaches 0 from the right of x, or the square root of x times the natural log of x. If we just straight plug in, okay, we can see that when you plug in for the radical, you should get 0. Whoops. You should get 0. And then here we would have times. Now, as, excuse me, as you approach 0 from the right for natural log, that is going to go to negative infinity. And if you think about a quick natural log graph, looks like this. So as you come at 0 from the right-hand side, you're going to see that your y values are approaching negative infinity. So that is an indeterminate form. I can't do any kind of Lhop. What I have to do is I got to try and rewrite this thing so I can get it into a form where I can possibly use my Lhop. So I keep my limit statement, x approaches 0 from the right. And it said that anytime you have some sort of 0 times some form of infinity, you're going to want to take one of those terms, just kind of bring it down to the denominator, reciprocate it, okay? So for me, I think that I'm going to bring down this, because working with natural log and putting it to the negative first power is just going to be kind of annoying. So what I'm going to do is I'm going to rewrite this as the natural log of x divided by 1 over the square root of x. Okay, 1 over the square root of x. So now what I do is I go ahead and I plug in my values. So at the top, that's going to give me negative infinity if I plug in 0 from the right. And at the bottom, as I approach 0, hopefully you know that that is going to also approach infinity. 1 over some number here that is going to consistently get smaller and smaller and smaller means that the whole thing gets bigger and bigger and bigger. So therefore, we can say that the limit as x approaches 0 from the right of the natural log of x, that's equal to negative infinity. And then the limit as x approaches 0 from the right of 1 over the square root of x, that's equal to positive infinity. So again, infinity or negative infinity over infinity, we know that Lhop is going to apply here. All right, so I am going to go ahead and I think the first thing that I'm going to do is I'm going to kind of write this for some convenience. So this is the natural log of x over x to the negative 1/2. So now I will Lhop here, and I will now have the limit as x approaches 0 from the right, and this is going to be 1 over x, and as a matter of fact, we need to be d dx. Okay. The limit as x approaches 0 from the right of d dx of the natural log of x to the negative 1/2. Okay, we know the limit as x approaches 0 from the right. Derivative is 1 over x divided by, this is going to be negative 1/2 x to the negative 3/2. So I am going to rewrite this for a little bit of convenience. The limit as x approaches 0 from the right of negative 2x to the negative first over x to the negative 3/2. So I'm going to just continue to rewrite this to help me out here. Maybe I don't have to use L'Hopital again. The limit as x approaches 0 from the right, this is going to be negative 2x to the positive 3/2 divided by x. And then I should have the limit as x approaches 0 from the right, and this is going to be negative 2x to the 1/2 power. And it looks like now I should be able to go ahead and plug in 0 and get 0 to the 1/2 power is 0, and then 0 times negative 2 is going to be 0. And we have successfully completed number 1. All right, let's move on to example number 2. The limit as x approaches 0 from the right of cotan of 2x times the sine of 6x. So if I plug in 0 here, that gives me cotan of 0, that's infinity, multiplied by sine of 0, which is 0, so that's infinity times 0. So that is this form right here. So maybe what we want to do is we want to help ourselves out, and maybe, just maybe, we may want to rewrite this guy. I'm thinking we'll do the limit as x approaches 0 from the right of sine of 6x divided by tangent of 2x. The reciprocal of cotangent is 1 over tangent, which is the same thing here as if I put tangent of 2x into the denominator. All right, so let's see what happens now if I plug in 0. 0 in the top becomes 0. Tangent of 2 times 0 is 0, which is 0. So yes, the limit as x approaches 0 from the right, okay, of the sine of 6x equals 0. And the limit as x approaches 0 from the right of tan of 2x also equals 0. Therefore, we know Lhop applies. And you guys saw me do this way back when we were in Unit 1 and we were doing L'Hopital's rule then. We just have to state here that Lhop is going to apply. So now we have to make sure that we ddx. So the limit as x approaches 0 from the right, ddx of the sine of 6x divided by tangent of 2x. And as you can see, the limit as x approaches 0 from the right is going to be 6, the derivative of sine is cosine, so this is going to be 6 cosine of 6x divided by the derivative of tangent is secant squared, okay, and then times by the derivative of the inner portion is 2, so 2 secant squared of 2x, okay? And then here, plug in your 0, should get 6 over, plug in here, secant of 0 is 1, 1 squared is 1, and then times 2 is 2. Final answer is just 3. Got to know your unit circle for that one. Okay, next one. So here, we have the limit as x approaches negative infinity. So we plug in, this is going to be plugged in for x, just gives me negative infinity times e to the negative infinity, okay, which is the same thing as negative infinity times 1 over infinity, which is basically negative infinity times by 0. The bigger the denominator gets in the fraction, the smaller the actual number gets, and it is approaching 0. So I'm thinking I will probably take the e to the negative x to the denominator, the limit, okay, or the e to the x, as x approaches negative infinity is equal to x over e to the negative x. Now you might be asking, why is he doing this? Well, again, this is 0 times some form of infinity, so I want to divide. Okay, so I got to get rid of that times and I got to get it into some sort of division here. So if I do this, if I plug in, this is what? Negative infinity. And then if I plug in negative infinity there, that's going to be e to the positive infinity, which that means it's going to infinity. So therefore, we're a check, we're a go. So we know that the Lhop is going to apply here. So I will now make it official and write the limit as x approaches negative infinity of x is equal to negative infinity. And then the limit as x approaches negative infinity of e to the negative x is also equal to some form of infinity. Therefore, Lhop applies. All right, so the limit as x approaches negative infinity of d dx of x over e to the negative x, okay? The limit as x approaches negative infinity, okay, is going to equal to 1 divided by negative 1 over e to the negative x power, okay, and then I will do the limit as x approaches negative infinity. This is going to be negative 1 e to the x power, okay? So just keep in mind if you need some kind of a visual here, all right, for this, okay, e to the x looks like this. And as you approach negative infinity, you should see that this is going to approach 0. So essentially, that is what it looks like. Not really sure, and I just caught this right now. That should be negative x, not negative infinity. It should be negative x. Feel free to plug it in there if you want to, but nonetheless, okay, a nice little graphical representation should work as well, and we should get 0 for that one. All right, that is example number 3. We are rolling. Okay, let's hit up example number 4. Now we are going to work with indeterminate form infinity minus infinity. This says that we want to create some difference here in LCD. So as we plug in 1, that becomes 1 over the natural log of 1, which is 0, and 1 over 0 is going to be infinity, minus 1 over 1 minus 1, again, is 1 over 0, so this is infinity. So now we have no choice but to create a common denominator. My common denominator is going to be ln of x times x minus 1, so the limit as x approaches 1, and my common denominator here is going to be ln of x times x minus 1, ln of x times x minus 1. And then this should be x minus 1 up top, and this should be ln of x up top there. And then I'll put it together as one fraction should look like that. And now I will go ahead and I will now start working on the fact of whether or not, now that I have a fraction, if I should be able to Lhop. Let's punch into the top. Okay, in the top, if I plug in, that's going to be 1 minus 1 is 0, minus 0, so that's 0. And plug into the bottom, the natural log of 1 is 0. And then 1 minus 1 is 0, so this is going to be 0 over 0. So Lhop is going to apply. So just make sure that you write down that your Lhop applies, but just like before on these other ones, I just want to save some time here. Make sure that you are including that, okay? Make sure that you are including this. Okay, the graders are going to want to look for that you know that Lhop applies, okay? So as I move further into these notes, I'm just going to make sure, I'm just going to sort of say, all right, I'm just going to do this part right here, which now means Lhop applies, and then you need to actually write it out further, okay? All right, so what we're going to do here is I am going to have you work this one out, okay? And um, or take the derivative here, and let's go ahead and have us do that. X approaches 1. This is going to be 1 minus 1 over x, and then this is going to be, let's see, product rule down at the bottom. All right, now we have to plug in again. Looks like once again, this is going to be, if you plug in 1, you get 0 over 0. Okay, and then what I'm going to have you do now is to, again, write down the limit as x approaches 1 for both numerator and denominator, and just verify that Lhop applies. Okay. And then I'm thinking I will go ahead and I think I'll just take the derivative as I see it here. Yeah, I think I'll just take the derivative. Okay, no reason to rewrite anything. Just kind of take it as it is. All right, so the limit as x approaches 1, derive the top. Okay, derive the top should give you 0 minus, that's going to be 1 over x squared over, okay, looks like I have a product rule again. So this is going to be negative 1 over x squared times x minus 1 plus 1 over x times by 1, I guess. I can put the 1, I don't really need to, plus another 1 over x. Let's plug in again. Numerator is going to give me 1. Denominator is going to give me, let's see, that's going to be negative 1 times by 1 minus 1 plus 1 over 1 plus 1 over 1. Hopefully you should see that that equals 1 over 2. All right, and that is the answer for that one. I think we're going to end there. That'll be part 1, and then I think we'll finish up with a part 2. Mr.